All right, let's do some alternating series today. So alternating series, I keep hinting at alternating series as we were going through with those negative ones in there. So this is what we're going to do with our alternating series test. Now, I'm going to load you up front with a bunch of theorems and definitions, and then we'll put it into play. All right? So that's the setup of what we're going to do. The first thing that I'm going to talk about here is absolute and conditional convergence. Okay, if an absolute is literally the absolute value. If I have a series and I take the absolute value of that series, so these are absolute value bars. If that converges, if the absolute value converges, then my actual series converges absolutely. All right. So there's something called absolute convergence implies convergence. All right. So I'm going to put that actually in parentheses because that's a common saying. Absolute convergence implies convergence. So it converges absolutely. That doesn't even look like a word. Let's try that again. Okay. So if the absolute value, so if I take the absolute value, meaning I'm getting rid of that negative sign, right? If that converges, then my entire series converges absolutely. Now, if the absolute value diverges, all right, so those are absolute value, I want to make sure, and my actual series converges, then the series, and I'm going to scoot it down here just a little bit, converges conditionally. Okay, so if I have absolute convergence, so if this converges, if I take the absolute value, then the whole thing converges absolutely. So let's highlight that. It's absolute, converges absolutely. If my absolute value diverges, but my series itself converges, then it converges conditionally. Now here's how that can happen. We haven't talked about it yet. We haven't talked about it yet, but we will here very shortly. If your absolute value diverges like this, then to determine this part, we're going to use the alternating series test. So you are only going to use, in reality, you are only going to use the alternating series test to determine conditional convergence. All right, that's it. So you're only going to use your alternating series test just simply to determine conditional convergence. All right, so now we know this. Now let's talk about that alternating series test. So you have that test under your belt, and then we'll push forward and see what's going on with it. Scoot this up. Theorem 10.16, which we know is bogus. We'll write it down. Alternating series test. So with my alternating series test, here we have the alternating series of -1 to the k plus 1 a sub k converges provided these criteria are met. There are two. Criteria number 1, the terms of the series are non-increasing. Oops, that's a number 1. So basically what we're saying here, if my terms of my series are either staying the same or going down, right? That's what we want to know here. Non-increasing. Criteria number 2, that my limit as k approaches infinity of a sub k equals 0. So notice my limit approaches infinity of just a sub k, not the alternating part, just the a sub k part. That part we want to determine if the limit is going to approach 0. Is it decreasing or non-increasing? And does my limit? If those two criteria happen, then my alternating series converges. So we are going to use our alternating series because it doesn't determine absolute convergence. This does not determine absolute convergence here. So I just want to know the terms of my series here, a sub k, that's the series that we're talking about, is non-increasing, is what we have. All right. So as long as those two criteria work, then I can come up with conditionally converge. Okay, let's do this thing. We are going to practice. Oh, wait, one more thing. Woo, I almost forgot. Okay, last but not least, if I have, using the alternating series test, here I have theorem 10.17, which we know is bogus, but alternating harmonic series. So you know, whenever I have these different series here, so we know if we have something that's harmonic, that's where your p is equal to 1, and that diverges. However, the alternating harmonic series converges. Okay. That is, if I have my series, k is going from 1 to infinity of -1 to the k plus 1 over k. This converges. All right, so let's do a little quick side check over here. If I'm going to look at this, because if you were to take the absolute value of this, then you would just have 1 over k, we know that diverges. All right. So if that diverges, we know it's not absolute convergent, so then we check here. If I have this, my a sub k here is equal to this 1 over k. Criteria number 1, is this decreasing? Or non-increasing, basically, but is it decreasing? Does it? A 1 over k? Yes. The denominator grows faster than the numerator. Number 2, if I'm looking at this, I want to know is my limit as k approaches infinity of 1 over k equals 0. Yes to that criteria also. So do you see what just happened here? It is decreasing. My limit equals 0. Therefore, by the alternating series test, this converges. And we just know that's just a common one. If you have an alternating harmonic series, then it converges. And this is the beauty of alternating series. Sometimes if you have a series that was just like a regular series, it would not converge. But if you make it alternating, all of a sudden it does converge, which is cool, right? All right, now let's do some examples here. So for your homework, and we're going to do these two right here just so we can practice it, we're going to practice using the alternating series test. Okay, we're going to practice using the alternating series test. No, in reality, we're going to determine conditional convergence with this, but I want you to practice figuring out this test so that when you do need to use it, then we have that at our disposal to use, all right? So here's example 1a. I have this series. K is going from 1 to infinity of -1 to the k plus 1 over k squared. So with that being the case here, let's make this a little bit nicer, shall we? So negative 1 to the k plus 1 all over k squared. So if that's going to be the case here, then do you guys know what's happening with this? So just in your head real quick, take this absolute value. If you absolute value and you get rid of this, you have 1 over k squared. Is that going to converge? Yes, right? So absolute convergence implies convergence. That's what we would normally do with this problem. So keep that in mind, right? So in reality, that is the approach we would take. But my goal right now is to just practice using this just so that we have a chance to practice this. Okay. For the alternating series test, I know that a sub k here is going to be 1 over k squared. Criteria number 1, is this decreasing? Yes. The numerator grows faster than the denominator, right? So it is. Criteria number 2. What do you know about the limit? That equals 0. So yes, this criteria, whoopsie daisy, is also true. Therefore, this series, okay, going from 1 to infinity, converges by the alternating series test. Right? 3 criteria in your statement. The fact that you have a series, whether it converges or diverges, and how you know that. But you, like what we just talked about, if we were to take the absolute value of this, you get this 1 over k squared. We automatically know that's convergent, so absolute convergence implies convergence because of the p series, right? But that aside, we're just going to do a little practice here using this alternating series test. Okay, let's practice one more. I have the series from 2 to infinity of negative 1 to the k, natural log of k over k. All right? So a sub k, oopsie daisy, is equal to the natural log of k over k. Step 1, is this decreasing? Now, this isn't a polynomial, right? If I'm looking at this, then this is not a polynomial that we're looking at. So what is another way to determine this? If the denominator grows faster than the numerator. Do we know that if I'm to come over here, here is my natural log function. Here is my identity function. Which one gets bigger faster? Yeah, the identity function, right? So that tells you your denominator is growing faster than your numerator. This one kind of almost levels out, but not quite. It just barely increases, right? So yes, denominator grows faster than the numerator. The other thing you could do here is to take that derivative, right? That's a pretty easy derivative to take. You could take the derivative. If your derivative is negative, then that also works. Well, let's just do that for fun. So if y is equal to the natural log of k over k, if I were to take this derivative, then the derivative of the first term is 1 over k times the second minus the first times the derivative of the second, which is just 1, all over the bottom squared. So I now have y prime is equal to 1 minus the natural log of k over k squared. If I just have it as 1 here, right, I'm looking at this 1, then this natural log of k is obviously getting bigger and bigger than 1. So my numerator here is going to be negative as k is greater than 1, right? So, or 2, honestly, because my value here is 2. So that's another tip off that this is going to be negative. Negative derivative, so decreasing. Let's try this again. Derivative, so decreasing. Okay. Either way, this in my book is just as easy to do, and we know enough about these graphs in order to pull that off. Step 2. Oh man, I used a lot of room there. The limit as k approaches infinity here of the natural log of k over k equals 0. Well, come on, people. If we know that this decreases, what does that tell you? That the denominator is going to grow faster than the numerator? And then what is that the same thing as? Right? That's your limit approaching 0. Otherwise, the denominator wouldn't grow faster than the numerator, and that's a moot point. So yes, this is also true. Meaning, therefore, the series converges. If one of those criteria were not met, then we don't know that it diverges because that's not part of the alternating series test. Here, let's swing it back. Your alternating series test only talks about convergence. You cannot determine divergence from this.